Okay, so we will continue with our lecture. So now we will start a new application. So don't forget that we are still studying uncontrolled rectifiers. The third circuit we have in uncontrolled rectifiers is single phase full wave rectifier supplying an R load. So we have a single phase full wave rectifier and it is supplying a resistive load. So how we can analyze this? So let's start by a quick introduction to understand how it will be a full wave and how they connected the circuit. So if we go to the single phase half wave, so we have a source and this source is AC and we have a load and we need this load to be DC. And DC means we need the polarity here to be fixed, while the polarity of the AC source is changing. So the AC source here has two periods. It is positive or negative. So when the source is positive, so this is the AC, it means this is positive and here is negative. And when the source is negative, we have here negative and here positive. So what we did, we connected this point to this point and we added here the diode. So what the diode will do, when the source is positive, the diode will be forward biased and this positive will appear here. And as you can see here we have positive and here we have positive, so the polarity is preserved. Now when the source reverses to be negative, this diode will be blocking, and if the diode is blocking, it will be open circuit, so this negative will not appear on the load. So the load will see only the positive cycle without seeing the negative cycle. So when we look at the load, so the load has only the positive wave will pass through the diode, and during the negative, the diode will open, leaving the circuit open, so V out will be half wave. So this is a case for half wave rectifiers. Now, based on this idea, we can come up with a very good concept or very good connection. So we need to keep this terminal positive, while this terminal of the source will be positive for half cycle, and then it will switch to negative in the second half cycle. So the idea is, let's connect a forward biased diode and let's connect a reverse one. So what will happen if the source is positive? This diode will be forward and this diode will be reverse. So when this is positive, this one will be forward and this one will be reverse, which means that the positive will go through this diode here and this terminal will be positive. Now when the source is negative, so here we have a negative which will make this diode reverse or open circuit, and if we have a negative here, this diode will be forward and this negative will go to the negative, which means the positive cycle will go up while the negative cycle will go down. And we can do the same here. So here, when it is positive, I need to connect it up, and when it is negative, I need to connect it down. So if this terminal is positive, this diode will take it up here, and when this terminal is negative, this diode will take it down here. And we have this well-known connection, which we call it a bridge. So this well-known connection is called a bridge. So the use for the bridge I don't know what is the issue. So the use for the bridge is to keep the full wave, okay? So as you can see, the bridge has 4 main terminals: 1, 2, 3, 4. So these are the terminals for the bridge. This side from the bridge is AC. That's why we can give it the symbol AC. And this terminal is positive and this terminal is negative. So if we sketch the bridge here, this is the bridge. So the bridge has 2 AC terminal and will give you 2 DC. And inside the bridge here, we have 4 diodes. And this is a connection for the bridge. So let's see a commercial bridge. This is one of the commercial bridge. Okay, this is the part number. Okay, just forget about the company. Okay, we just taking this as an example. So as you can see, this is a rectangular shape. Okay, and you can see here is a positive, here is a negative, and here is a 2 AC. And usually the AC are the 2 inner pins, and the DC are the 2 outer pins. This is a common layout or pin out. And usually the positive has this part here, this angle here. So you can look for the outer pins to be the DC, and on this side, on this edge, it is the positive one. And here you can read the values here, that the current is 20 amperes. Each model of these, so 20 has 200 volt, 40 has 400 volt, 60 has 600 volt, 80 has 800 volt. The one time or the surge current is 240, the reverse leakage is 10 micro, the forward drop voltage is 1 volt. Okay, so if you sketch the characteristic of the diode, so here is I, here is V. So this current here, the reverse leakage current, is 10 micro ampere. The forward voltage here is 1 volt. We said that we will consider this to be 0, and we will consider this to be 0 if it is ideal. Again, each model and its rated voltage. Here is the RMS, is simply the maximum divided by √2, as we will see, similar to sine wave, and the maximum is the DC also. And this is one interesting point here, is the forward current has 2 rating, 20 amp and 3.5. okay, don't forget that here it is mentioned that this bridge has 20 amp. Okay, but if you read through the data sheet, you can see that this rating 1, which is the 20 amp, if you are using a heat sink. But if you are not using a heat sink and you just adding this bridge into a PCB, so without a heat sink, the maximum current will drop to 3.5. okay, it's almost 1/8 is a value. Okay, so you are getting 1/8 as a value if you don't use a heatsink. So sometimes a heatsink can increase the rating with in this case it's multiplied by 8 just using the heatsink. So pay attention which values you are reading, and if this value here, which is in this table, this is a rating, okay? Because the value here is written as 20, but if you read through the details, this 20 is with heatsink, okay? So you have to add an aluminum heatsink. So this is a bridge, okay, as you can see. And the common sketch that we use for the bridge, this is the way that we sketch the bridge. So we sketch 2 diodes here, and we sketch another 2 diodes here. The top is connected to the positive of the load. The bottom is connected to the negative of the load. And between these 2 diodes, this is AC. And between these 2 diodes, this is the second AC. So if the AC is positive wave, so this positive will go through this one. So if the diode has positive negative, it is forward. If the diode has negative positive, it is reverse. If the diode has negative here, it is forward. If the diode has positive here, it is forward, okay? So at the positive side, we are looking for positive, and at the negative side, we are looking for negative. So this positive here will turn this diode on, and it will be connected here. This negative here at the same time will turn this diode on and will be connected here. When the supply reverse to be negative, so this negative here will conduct the lower one and go to the load. And this case here will be positive. This positive here will connect this one and will go to the load. So the top terminal will be always positive and the lower terminal will be always negative. And this is the conversion from AC to DC through the rectifier. So if you can look here, just to prove it is the same connection. So here, this is the AC point connected to one positive and one negative. So the AC point is connected to one positive and one negative. Then the positive is connected to the top and the negative is connected to the bottom. So the positive is connected to the top and the negative is connected to the bottom. So this connection is the same as this connection, just different way to sketch it, okay? So we call this connection the full bridge, and we call this circuit the full wave rectifier. Okay, so we call this circuit the full bridge. So we call this circuit full bridge, and we call this application as full wave rectifier. So we have the half bridge and we have the full bridge. So half bridge, which is the half wave rectifier, and full bridge is the full wave rectifier. So the first application, as we mentioned, so this is just the introduction. So we have single phase full wave rectifier supply R load, and we need to do the analysis in this case. So in this case, we have 4 diodes. And we have our AC source, and this is a jump. It is not connected here. So here is the load. Now the naming of the diodes is very important. So we name the diodes diode 1, then here we have diode 2, then here we have diode 3, and here we have diode 4. So this is the naming 1, 4, 3, and 2. So you have to write the naming like this because this is the sequence of conduction between them. And this is the AC source. Here we have positive and negative for the DC source or the DC output. So here we have voltage V out, current I out. Here we have voltage Vn, current I source. Here we have V diode 1. So don't forget that the diode voltage is going from the negative to the positive. So here is V diode 1. Here we have V diode 3. Here we have V diode 4. Here we have V diode 2. The direction for the currents. So here we have I diode 1, I diode 3, I diode 4, I diode 2. So the directions for the diode. So current is going in this direction, in the direction of this arrow, and voltage from negative to positive. So this is V diode and this is I diode. So in this case, we need to sketch V out, I out, Vn, I source, and we need to sketch V diode 1, V diode 2, V diode 3, V diode 4, I diode 1, I diode 2, I diode 3, I diode 4. So we need to sketch every single variable, okay? So we are not going to do all of them, but you will be able to do this, okay? Just we will discuss some of them and you will be able to do all of them. Now, let's see how we will analyze the circuit. So we are able to sketch the waveforms, and after we sketch the waveforms, we will do the derivation for the average and the RMS. So as we mentioned before, we will analyze the circuit into two situations, okay? When diodes are on and which diodes, and when the diodes are off and which diodes. So let's sketch the circuit here to see what we mean by this. So we will take the circuit in two cases. So the first case, when the source is positive here, negative here. So let's keep the positive line green and the negative line red. So when the supply is positive, try to use smaller one. So when the supply is positive, so this point is positive. If this point here is positive, it will make this diode forward, okay, and this diode reverse, which means this one will turn on, keeping the positive up, and this diode here can be removed because it will be open circuit. And for the negative one here, if we have negative at this terminal, this negative is connected to a negative, which will make this one conducting, and this one will be disconnected. So it will go down to the output. And in this case, the diode here is simply disconnected and it is open circuit. So in this circuit here, we have diode 1, diode 2 are on. That's why we numbered them as 1 and 2, because they turn on together. Diode 3 and diode 4 are off. And you can see that during this case, I source is going through diode 1, is going through the output, is going through I diode 2. So this is I diode 1, I diode 2, I out, and V diode 1 equal V diode 2 equal 0 because they are conducting, they are short circuit. If you do KVL, V input will equal to V out, V in equal to V out. And if you do KVL here, here is V diode 3, voltage here is 0 volt, voltage here is V out. So if you take this loop and you do KVL here, you can see that V diode 3 equal to V diode 4 equal to negative V out. Okay, and you can do this from KVL. So these are the equations we have during the positive half cycle of the source when the source is positive. Now when the source reverse direction during the negative cycle of the source, in this case here we will have negative and here we will have positive. So the negative will forward bias this diode and it will go down to the negative. The positive here will forward bias the top diode and it will go to the positive here, which means that this diode is disconnected and this diode is disconnected. So here we have open circuit and V diode 1. Here we have open circuit and V diode 2. So in this case, diode 3 and diode 4 are on, diode 1 and diode 2 are turned off. You can see here I source is going in this direction, or actually the current is going out. Okay, so in this case, I source equal to negative I diode 4 equal to negative I diode 3 equal negative I out. So I out is going down, then it is negative I source. I diode 4 is negative I source. I diode 3 is negative I source. Make sure cancel. And if we find what is V out, okay, you can see here is V out, here is Vn, and V out plus Vn. If you do KVL, V out plus Vn equals 0, or V out equal negative Vn. So these are the equations we have. And diode 3 is on, so it's short circuit. Diode 4 is on, so it's short circuit. So V diode 3 equal V diode 4 equal 0. Now if we do KVL here, V out plus V diode 2 equals 0 if you do KVL in this loop. So V out plus V diode 2 equals 0. So you can find that V diode 2 equal V diode 4 equal negative V out equal positive Vn. So these are the important equations we have in this case. So this is the first one, this is the second one, third one, and here is the fourth one. And these are the equations in this case: first equation, second equation, third equation, and fourth equation. So these are the equations for the positive half cycle of the source and the negative half cycle of the source. So if we go and start to sketch, so I will start by sketching here omega t, V input of t. As we mentioned, we will use 3 squares as pi over 2. So here is pi, here is 2 pi. It will be maximum here, 0, 0, 0. So we can sketch the sine wave for the input. Here is Vmax, here is minus Vmax. Now, during this time, we have diode 1, diode 2 on, okay? And as we mentioned, we can specify when the diode is on, but we cannot tell when it is off until we sketch the current. Please don't fail into this trick. So the diode will turn on when it is forward biased, but it will not turn off unless its current goes to 0. Now we can sketch. So we can sketch V out. So during the positive half cycle here, we will apply set of equations 1. So here we have Vn equal V out. So I will take this waveform and I will sketch it down here. And this is Vmax. Let's keep consistent. So the peak here is 2 squares Vmax. And we can sketch I out of t. So we have a resistive load, and we mentioned this, we have a resistive load. And resistive load means that I out is V out over R. So the shape of I is the same as the shape of V, just scaled by R. So if we sketch I out here, it will be the same shape as V. So here it will be 0. And its maximum will be V maximum over R. And now we know that the current is 0 at this point. So we can go up and close here and say the diode will be operating up to this point. So at this point, the diodes will turn off. So the diode will turn on when it is forward bias, and it will turn off when its current goes to 0. Now we can sketch also I source. So I source equal to I out. So I source equal to I out. So what we will sketch is the same here. This is I source. Here Vmax over R. And we can sketch I diode 1 or I diode 2 or I diode 3. Just you are following these. Okay, so let's sketch I diode 3, for example. I diode 3. So during this time, diode 3 is off. So I diode 3 equal to I diode 4 equal 0 because they are open circuit. So during this time, I diode 3 is 0. We can also sketch any voltage of diodes. So let's sketch, say, V diode 4, any voltage. So V diode 4 during this time, V diode 4 equal negative V out. So V diode 4, we will take V out here during this time, and we will take it negative, so we will reverse it. So V diode 4 equal negative V out, I diode 3 equal 0, I source equal to I out equal V out over R, V out equal V source. These are the equations we have. So as you can see, diode 4 during this time is off, is open circuit, and when the diode is off or open circuit, it is reverse biased. And you can see here that the peak inverse voltage is Vm. So this is negative Vm, so the peak inverse voltage is negative Vm. Just I will remove this so we can continue sketching. Now we will go to the second period here, or the second time. So we will apply here equations 2, and here are set of equations 2. So during this time, V out equal negative Vn. So what I will do, I will take Vn here, but I will reverse it. So V out will equal this value, but negative. So what I will do, I will reverse this wave. So here is Vm. And you can see, this is a repeated pattern, that V out has full wave. So each half cycle you have a wave. You don't have a wave, then zero, then a wave, then zero. This is half wave. But this case is full wave. That's why we call it full wave. And I out is V out over R. So simply I out, I will take this V out and divide it by R, because this is Ohm's law. So this is V max over R. So I out equal V out over R. Okay, just I will repeat it here because this is a repeated pattern. V max over R. I source equal negative I out. So as you can see here, I source is negative I out. So I will take I out and I will sketch it negative. Okay. So as you can see that I source is AC. And this is great news. You should be happy. Okay. If you look here for the first case, if you sketch I source here, I source is I out, okay? So if you look at I out is positive, then zero. So here I source is DC, and this is something should make you sad. Why? Because this I source is going through a transformer, and you know what is the effect of having a DC taking out from a transformer. So adding a transformer here is questionable, okay? I don't agree on this. Even if the reference is doing this, but I don't agree. Okay, so let's continue. Now we can sketch also I diode 3, because I diode 3 here is negative I source, or it is I out. So I diode 3 is I out. So I will take I out and sketch it here. Sorry, the two graphs intercepted here. So here is V max over R, then it is 0, and so on. And to sketch V diode 4 during this time here, V diode 4, so this is not correct. So this is V diode 1. V diode 1. So these two voltage between are equal, V diode 1 and 4. So during this time, diode 3 and diode 4 are on. So V diode 4 is 0, because diode 4 is on. So here, V diode 4 will be 0. So whenever a diode is on, V diode is 0. Diode is off, V diode is negative. Can you see a positive voltage on V diode? So can I sketch V diode and I see a positive voltage like this? Can this happen? No, this contradicts with the idea for the diode. So the diode characteristic IV, that its voltage when it is on will never exceed 1 volt. So the voltage, if the voltage is positive of the diode will turn on and its voltage will be 0. So when we see positive waveform for V diode, we know that you should get 0, okay? So now we finished sketching the waveform for V source, for V out, for I out, for I source,